We've already seen how when we start with a differential equation and we solve this differential equation, we end up first with a general solution, which is which gives us a family of functions. Okay, and one way that we can represent this family of functions graphically is to use what are called slope fields. Okay, so that's what we're going to look at today is how can we visually graph a whole bunch of functions at once, or all of the possible functions that satisfy a particular given differential equation. Okay, so what we're going to do is we're going to go through a bunch of ordered pairs, and the ordered pairs are already listed in a chart here for us. And we are going to identify what the slope of some function y equals f of x. Okay, so this is the y equals f of x, whatever this function happens to be that's a solution to this differential equation. We're going to go through and figure out what is dy over dx, or what is the slope at each of those ordered pairs. Okay, and then if you think back to when we first introduced the derivative, we started with a quadratic function. I think it was like y equals x times the quantity x minus 2 or something like that. And we started by drawing little tangent segments at various integer points along that curve to get an idea what the slope at each of those individual instantaneous points would be. And so we're going to have something similar here where we have a whole bunch of small line segments that represent the slope at each of these ordered pairs. Okay, so one way to do this is to start with a table and fill them all in and then graph those slopes after we have a table. Now, on a homework problem or a quiz problem or something like that, you're not going to have nearly as many points as what's on here, but this is going to give us a good picture of what the slope field looks like. Okay, so starting with, our derivative is dy over dx equals 2x, which means the slope at every point is twice the x coordinate, okay? This is the third time we've used this particular differential equation as an example, so we should be pretty familiar with what this is going to look like already. Okay, so when we have the point -3, -2, twice that x coordinate is -6, so that means my slope is -6. At -3, -1, again, slope is -6. At -3, 0, again, the slope is -6. And we can see that anywhere the x coordinate is -3, we have a slope of -6 because this derivative is only dependent on the x coordinate. Okay, and then for all of these points where x is equal to -2, then twice that is -4. So our derivative is -4 for all of these. Okay, when x is -1, twice that is -2. Okay, when x is 0, twice that is still 0. When x is 1, our slope is now +2. Okay, and once you see a pattern, you can probably fill these out pretty quickly. When x is 2, we have a slope of 4. And when x is 3, we have a slope of 6. Okay, so what we're going to do now is draw little short line segments that have these slopes on our graph. Okay, now I'm not going to, I'm going to have to go back and forth between the table and the graph here, but hopefully you have it in front of you. So whenever x is -3, which is these 5 points here, we had a slope of -6, and we have little tiny squares on here. So if you want, you could actually, count up and left and down and right by 6 on each of these. But I just know that's going to be a very steep negative slope. So I'm going to draw a segment that looks something kind of like that. And then again, for all of the other values. Okay, so those are about all the same. And then when x is equal to -2, remember our slope was -4. So still pretty steep, but maybe not quite as steep. Okay, and if I want to, I could, count 1, 2, 3, 4. Like I could be counting the points, but this is really, it's more about a comparison in relation to each other. So a little bit less steep here. Here we have a slope of -2. Okay, here we have a slope of 0 at all of these points. So little horizontal segments. Slope of +2. slope of positive 4. You can see I'm not really being super careful about this. And then a slope of positive 6. Okay, what we have here is a slope field, and this is representing all of the functions that satisfy this differential equation, dy over dx equals 2 times x. Now, we already know this to be the function or the group of the general solution or family of functions y equals x squared plus c. So we should have a representation of all of the functions that satisfy y equals x squared plus c, or in other words, all of the parabolas that have a vertex that is on the y-axis and then with some kind of vertical shift. So if we were to try and trace a particular function through here, so let's say we're talking about the function that passes through, that has a vertex at 0, -2. Well, here I have a horizontal tangent, so I know that I either have a max or a min or an asymptote right there. And then to the left, the slope becomes positive, and the further I move to the left, the more steep that slope becomes. So something, so something kind of like that. And then same thing over here. The further to the right I move, the steeper that slope becomes. So something on that side. So y equals, this would be something like y equals x squared minus 2. Again, that's because we already know what that function looks like. So this slope field gives us a good representation of the flow of those functions at any particular point. Okay. You're not going to have a curve that goes, that crosses through one of these little segment lines, because all of those segments should be tangent at a particular point. So you can see, and I missed a little bit, but right, if I were passing through that point, then I would have a slope that should be about parallel to that little tangent segment there. Okay, and then here, same thing up there. If I wanted to be even more accurate, I could plug in some fractional values, like I could plug in x equals 1/2, 1.5, 2.5, -1/2, etc. But really, just usually the integer values are going to be close enough. Okay, so this is what the slope field looks like without this on here. Okay, sometimes you might have to draw a curve through there, but most of the time that will be, you'll just be creating this or answering questions about this, or maybe even matching a slope field to a differential equation. Okay. All right, then this part down here says find the particular solution to the given differential equation with the initial condition f of 0 equals -1. This is stuff that we already did. We did this in 3.9. We already know that our differential equation has a general solution of y equals x squared plus c. I'm not going to work all that out because we've done this one a couple of times now. And so then remember, we plug in our initial condition. This is the ordered pair 0, -1. So -1 equals 0 squared plus c. C is -1. So the particular solution, which of these curves satisfies this initial condition? Y equals x squared minus 1. Okay. For this next one, go ahead and pause it and try and fill out this chart on your own, and then I'm going to go ahead and fill it out as well, and then come back and let's see if we have the same thing. Now, one thing I want to point out here is that this derivative is given implicitly, meaning your derivative or your slope at every point is not only going to depend on the x coordinate, but on the y coordinate as well. So the first one is going to be 1/2 times -3 times -2, which is +3. Okay, so go ahead and try and fill those out. Okay, do you have a table that looks like this? If not, then pause it and go back and check your multiplication here. Okay, and I will give you a hint. As you start, like after you do the first couple of sets, like where x is -3, then x is -2, you kind of see this pattern that will help you fill that in more quickly. Okay, all right, so we're going to go through and graph these now. And we're doing little line segments at each of these ordered pairs that have these slopes. So at the point -3, -2, -3, -2, I'm going to have a slope of +3. So fairly steep positive slope. Okay, so pause it, fill them out, and I'll do the same. Okay, do you have a slope field that looks like mine? Okay, hopefully yes. If not, erase it, go back, try it again. If I'm looking at the general direction of these, what I'm seeing is, switch back here. What I'm seeing is depending on which quadrant I'm coming from, it looks like I have something that is decreasing, but it is becoming less decreasing. And then since all of the points that would cross the y-axis have horizontal tangent lines, it looks like maybe we have another minimum here and then it continues upward like that. So maybe something kind of parabolic, but probably not exactly a parabola, okay? And when we see the equation, we'll see that that's true. So maybe something that comes down but then kind of flattens out and then goes up, something like that. Or if it's coming from down here, so in other words, if my initial condition is a point that's down here in one of these two quadrants, then I probably have something more shaped like that, okay? All right, so let's go ahead and look at solving to find the particular solution. So let me rewrite the equation, and I will go all the way through this one. dy over dx equals 1/2 xy. So first thing I'm going to do here is split. Actually, first thing I'm going to do is move this over. Okay. There we go. Is split these, and so I'll have 1 over y dy is equal to 1/2 x dx, and then integrate both sides, and there we go. We have the natural log of the absolute value of y. Remember, this is the new formula that we introduced in 6.5, day 1, okay? And then over here, I have 1/4 x squared plus c. Now, this is something that we haven't done yet. If you would like to solve for y first and then plug in your initial condition, you are welcome to do so. Okay, I'm actually going to do this 2 different ways. So I could solve for my initial condition, which is going to mean absolute value of y is equal to e to the x squared over 4. I'm going to condense that, plus c. Okay, and then to take the absolute value bars off there, I need a plus or minus. So y equals plus or minus e to the x squared over 4 plus c, and then I can plug 0, -1 into this equation. So I end up with, come up here, so I end up with -1 equals plus or minus e to the 0 plus c. Now, if this is a negative over here, I know I need a -1 as my coefficient. So I'm going to keep the negative, okay? Not the positive, because I want it to match this. And then e to the c needs to be equal to 1, so this means that c is equal to 0. E to the 0 is 1. Okay, so if c is equal to 0, then plugging that back into this equation, I have y equals, and remember we're keeping the negative e to the x squared over 4, and then I don't need to write plus 0. Okay, so here is my particular solution. In this case, I solved for y first, and then I plugged in my initial condition. On the next one, I'm going to do it the other way and show you how, if you're looking for a particular solution and not necessarily a general solution, then you can actually plug your ordered pair in earlier and still solve the same way. Okay? All right, but let's try one more slope field here. So same thing as before, we are using these ordered pairs, plugging our values in here to solve for, or to determine the slope at each point. In this case, the slope is purely dependent on the y-coordinate and not the x. So pause it and go ahead and find all of your slopes, and then we'll see if we get the same thing. Okay, hopefully your chart looks like mine. Again, as we're filling this out, since it's only dependent on the y-coordinate, then we see a pattern pretty quickly. Whatever the y-coordinate is, anytime that y-coordinate shows up, so this point, this point, this point, this point, this point, this point, and this point, then they all have the same slope, and then you can repeat. So you really don't have to do 1, 2, 3, 4, 5, 6. We don't have to do 35 different slopes. We can just do 5 and then know that those are going to repeat for all 7 values of y. Okay. All right. So then I'm going to go ahead and draw the slope field using these slopes. Okay. Pause it, draw yours, and then see if you get the same thing I do. All right. Hopefully you have something that looks like this. Here, the general flow of this seems to be that if we are above what appears to be a horizontal asymptote right here at y equals -1, we have curves that are coming downward, and so as x increases, then these are decreasing. So let's draw one in. maybe something like this. Okay. Oh, actually, it probably goes a little bit lower than that. Okay, maybe something like that. But either way, it does look like, or coming from below, something like this, it looks like we have either a decreasing or increasing function that appears to have a horizontal asymptote here. So I'm thinking maybe something logarithmic. Okay. All right, so let's go ahead and find the particular solution to the differential equation with our initial condition of the ordered pair 1, 0. Okay, so starting with our differential equation, let me rewrite this. dy over dx equals -1/2 times y plus 1. Okay, so first thing I need to do is rearrange things. I'm multiplying by dx. I'm only dividing by the y plus 1. I'm going to leave this here, and I cannot separate this, so I definitely don't want to distribute, but I'm going to keep this y plus 1 all together and divide both sides. So I end up with 1 over y plus 1 dy is equal to -1/2 dx. Okay, so when I integrate this, remember we talked about in 6.5 day 1 how the antiderivative of 1 over u du was the natural log of absolute value u plus c. Okay, so here this is the derivative of natural log. It also involves the chain rule though, so really we're looking at this y plus 1 being our u term. Okay, so this is u, du is 1 dy, which is what we have, so we don't need to manipulate the coefficients. So the antiderivative of 1 over u is natural log of u. So this gives us the natural log of the absolute value of u, so absolute value of y plus 1. Okay, and then on the right side, -1/2 x, or -x over 2, plus c. This -1/2 is just a coefficient. Okay, so to solve from here, again, we can solve for y first, which would mean take the exponential of both sides, put the plus or minus. In this case, we would have to subtract 1 as well. But for this one, I'm going to go ahead and plug my ordered pair in here to show you how this works. So I won't have the same value of c, but I'll have the same particular solution. So if I plug in the ordered pair 1, 0, I get the natural log of absolute value of 0 plus 1 is -1/2 times 1 plus c. Natural log of 1 is equal to 0. Okay, so that means that c is +1/2. So now when I plug this back in right here, I still don't have y isolated, meaning I'm going to have to do that algebra to solve for y at the end instead of at the beginning of the problem because I haven't written my general solution yet. So I end up with the natural log of absolute value of y plus 1 equals -1/2 x plus 1/2. So then to solve from here, take the exponential of both sides, we get absolute value of y plus 1, equals e to the -1/2 plus 1/2. Okay, take off the absolute value bars, put a plus or minus in front of there. We have y plus 1 equals plus or minus e to the negative, I'm going to write it as x over 2 just to make it a little bit shorter. Okay, -x over 2 plus 1/2, and then subtract 1 from this. So we have y equals -1 plus or minus e to the -x over 2 plus 1/2. But here's the thing, that can't be my particular solution because it's actually two different solutions. So I need to go back and check to see, do I need the plus or the minus here to satisfy the initial condition? Okay, so if I were to plug a 1 in right here, I would have e to the 0, -1/2 plus 1/2. So I would need 0 equals -1 plus or minus, and so this would be a 1 right here. I need this to be the positive 1, not the negative 1, so I'm going to keep that plus, meaning my actual particular solution is -1 plus e to the -x over 2 plus 1/2. Okay, so again, it doesn't matter whether you want to solve for y first, keep that plus or minus on there, and then solve and choose whether you want the plus or the minus when you plug your ordered pair in, or go ahead and solve for c first, plug it in, but you still need to check to figure out whether you need the plus or minus depending on your initial condition.